The intriguing physics behind levitating trains is explored, revealing how these advanced systems defy gravity. The cutting-edge engineering and scientific principles that enable maglev technology are demystified for the audience. Mind-blowing revelation. Imagine a train floating, not on tracks, but on a cushion of air, defying gravity as it speeds across the landscape. This isn't science fiction, it's the incredible reality of maglev trains. But how do these massive machines actually levitate? Get ready to have your mind blown as we demystify the cutting-edge physics that makes it all possible. What if I told you the future of travel isn't just about going faster, but about completely rethinking how we move? We're talking about trains that hover, frictionless, propelled by unseen forces. How can something so heavy simply float? Join us as we uncover the astonishing scientific principles and engineering marvels behind levitating trains. Forget everything you thought you knew about trains, because the next generation doesn't touch the ground. These aren't your grandfather's locomotives, these are engineering masterpieces that literally defy gravity. In this video, we're not just explaining the physics of levitating trains, we're pulling back the curtain on a technological revolution that's already here, and showing you exactly how it works. First step is to get the train off the ground. Maglev systems achieve this through powerful electromagnetic fields. Like poles repel, the basic principle is that magnets with the same polarity will push away from each other. Electromagnets in the tracks. The track, or guideway, contains a large series of propulsion coils. Magnets in the train. The underside of the train's carriages also has powerful The coils in the guideway act like a linear motor. Alternating polarity. The electric current supplied to the coils is constantly changed, which alternates their magnetic polarity. Pull and push. This creates a unique system of magnetic fields that attract the train forward from the front and push it from behind, propelling it forward. Sustained speed. The frequency of the alternating current is matched to the train's speed to maintain a continuous, smooth acceleration. Superconducting magnets. When certain materials are cooled to extremely low temperatures, they become superconductors with zero electrical resistance. Electromagnets made with these materials produce incredibly powerful magnetic fields. Levitation is the process of holding an object aloft in a stable position without any solid mechanical support. The concept, often seen in magic, science fiction, or religious texts, captures the human imagination with its promise of defying the most fundamental force of nature, gravity. On the surface, levitation appears to be an impossibility for a simple reason: everything with mass is subject to a constant downward pull. This seemingly unbreakable law is what makes a dropped apple fall to the earth and keeps our feet firmly on the ground. To overcome gravity's constant tug, a counteracting upward force is needed, and our intuition tells us that such a force can't come from nothing. This is why true levitation seems like science fiction. While stage magicians use wires and cleverly hidden platforms, and spiritual accounts remain unsubstantiated, the pursuit of genuine, unsupported flight has long captivated scientists and inventors. At its core, all magnetism is created by electricity. Magnetism is not a separate force but is, along with electricity, a feature of one of the universe's fundamental forces, electromagnetism. Magnetism in magnets. The magnetism in a permanent magnet, like the one on your fridge, is generated by the electrons in its atoms. Electrons are tiny, negatively charged particles. As they move and spin, they act like miniature magnets. In most materials, these tiny magnetic fields point in random directions, canceling each other out. In a magnet, most of these tiny magnetic fields are aligned in the same direction, combining to create one large, powerful magnetic field. Electromagnetism in wires. Electromagnetism is most apparent when you pass electricity through a coil of wire. The electric current, the flow of electrons, creates a magnetic field around the wire. By controlling the electricity, you can turn the magnetism on and off and even change its strength. Whether a magnetic force results in attraction or repulsion depends on how magnetic fields interact with each other. Imagine magnetic fields as invisible flows of energy, or field lines, that loop out from a magnet's north pole and into its south pole. Imagine each magnet is a crowd of people walking in the same direction, from one end, the North Pole, to the other, the South Pole. Attraction: when the north end of one crowd meets the south end of another, they can easily merge and flow together, pulling both groups closer. Repulsion: when the north ends of two crowds face each other, the people are pushed apart by the opposing flow of traffic. The crowds can't merge and instead force each other away. Heat fields resist merging. Trying to force two like poles together is like trying to squeeze two inflated balloons into the same space. The closer they get, the more the clashing fields push back with increasing force. Electromagnetic suspension, EMS, and electrodynamic suspension, EDS, are two different approaches to magnetic levitation, maglev. The main difference is that EMS uses an attractive force to pull the vehicle up toward the track, while EDS uses a repulsive force to push the vehicle away from the track. Electrodynamic suspension, EDS. Repulsive force: powerful superconducting magnets on the train induce opposing magnetic fields in conductive coils on the track. The resulting repulsive force pushes the train up. Electromagnetic suspension, EMS. Attractive force: electromagnets on the train wrap around a ferromagnetic guideway and pull the vehicle upward. Smaller gap: EMS systems operate with a smaller distance between the train and the track, typically about 10 to 15 mm. Active control: because the system is naturally unstable, it requires a complex, computer-controlled feedback system to constantly monitor and adjust the magnetic fields to maintain stability. Building and maintaining maglev tracks and trains involves complex and intricate engineering challenges far beyond those of conventional rail systems. While the frictionless travel offers high speeds, lower long-term wear, and quieter operation, it requires extraordinary precision, advanced technologies, and substantial capital investment. Alignment and structural precision. Minimal tolerance: maglev guideways, or tracks, demand extremely tight tolerances, typically within millimeters, to ensure stable levitation. This level of precision must be maintained over the entire route, which can span hundreds of kilometers. Power and magnetic systems. Linear motor integration. For high-speed maglev, the entire length of the track acts as a linear motor. This requires embedding electromagnetic coils along the guideway to provide propulsion, which is more complex and expensive than the simple rails of a conventional track. Precise control systems, sensors, and power management work together to ensure high-speed train stability and safety by continuously monitoring train and track conditions, providing real-time data for automatic speed and braking adjustments, and managing electrical power delivery for smooth acceleration and braking. Sensors gather data on wheel speed and track position, which control systems use to enforce speed limits, prevent derailments, and adjust traction to maintain stability. Power management systems ensure consistent, efficient power delivery, crucial for high-speed operation and stability. Automated control. Systems like positive train control, PTC, and automatic train control, ATC, continuously monitor train speed and location to prevent overspeeding and other accidents. Traction and braking. Control systems manage the traction, propulsion, and braking systems to maintain optimal speed and stability, preventing issues like wheel slip. For certain futuristic transport projects, such as maglev, magnetic levitation, trains and ultra-high-speed pods, specialized guideways are needed instead of traditional railroad tracks. This unique infrastructure allows for immense speed and efficiency, enabling these systems to operate on a truly massive scale. Megaregional connectivity. The speed and efficiency of guideway systems are necessary to connect vast geographic areas. India's Mumbai-Ahmedabad high-speed rail is a well-known example, a 508 km corridor with speeds over 320 km per hour. Though it uses traditional high-speed rail, it illustrates the scale of connecting major economic hubs. Massive freight and urban networks. Proposed guideway projects, such as the conceptual Global Guideway Grid, would move not only people but also a wide range of goods. This could potentially form a new global infrastructure utility, replacing or augmenting existing road and rail networks. Both monorail and maglev, magnetic levitation, train systems require specialized infrastructure called a guideway, rather than traditional dual steel rails. These projects are often immense in scale, requiring significant investment, and a transformation of urban transit landscapes. Connecting Tokyo and Osaka are decades-long endeavors that demonstrate the immense scale of construction, budget, and engineering required. National and regional transformation. When completed, these large-scale guideway projects can reshape entire regional economies and transportation networks by drastically reducing travel times between major hubs. The total guideway infrastructure for an extensive network can cover hundreds or even thousands of miles. Globally, there are 6 operational commercial maglev systems: Shanghai's high-speed Transrapid Line, the low-speed Linamo in Japan, and 2 systems in South Korea, Daejeon Rodam Maglev and Incheon Airport Maglev. China also operates 2 low-speed urban lines, and the Linamo is the only other commercial line besides Shanghai in the high-speed category. While the Shanghai Transrapid is the flagship example, other high-speed maglev projects like Japan's experimental Twiss Shinkansen have been proposed, but widespread implementation is challenged by high costs and infrastructure needs. Maglev technology, or magnetic levitation, offers significant advantages over conventional rail systems by using magnetic forces to lift, propel, and guide a train above its track. By eliminating physical contact, maglev trains achieve higher speeds, superior efficiency, and reduced wear and tear, leading to numerous environmental benefits. The future of high-speed intercity travel will likely see a continued expansion of maglev technology, while hyperloop concepts, despite recent setbacks, could still see specialized deployment. The 2 technologies present distinct trade-offs in terms of speed, cost, and practicality. Maglev uses powerful magnets to levitate and propel trains above a track, eliminating friction and enabling greater speeds than conventional high-speed rail. Having already been deployed commercially, maglev's potential for intercity travel is a matter of continued evolution, not radical invention. Hyperloop is a concept that builds on maglev by propelling pods through a sealed, near-vacuum tube to achieve ultra-high speeds, potentially over 1,000 km per hour, 620 miles per hour. While the idea has captured significant attention, its commercial feasibility remains in question due to major technological and economic challenges. Ultimately, while maglev is a proven technology continuing its evolution, magnetic levitation, trains promise high-speed, quiet, and efficient travel, but several major challenges, including extremely high costs and infrastructure incompatibility, have limited their widespread adoption. While maglev offers clear benefits like minimal friction and long-term operating efficiency, the immense initial investment and construction hurdles deter widespread deployment. Increased urbanization and rising demand for sustainable, high-speed travel are expected to continue driving demand for maglev systems. The integration of artificial intelligence and wireless power transfer could also boost efficiency and enhance the market. The high initial costs, combined with uncertain ridership projections, make it a challenging investment for both governments and private companies. Emerging research in materials science and quantum physics is poised to revolutionize levitation technology, moving beyond the high-energy demands and cryogenic cooling of today's systems. The key is developing new materials with extraordinary magnetic and optical properties that can enable stable, efficient levitation in a wider range of conditions. Quantum locking. This phenomenon, based on the principle of flux pinning, involves trapping magnetic fields within a Type II superconductor, holding it in place above or below a magnetic track. It creates a powerful, stable locking effect that is fundamentally different from simple magnetic repulsion. New materials could make this stable, frictionless motion more practical and widespread. We may one day travel using wormholes, teleportation, or antimatter propulsion, but these mind-bending possibilities are still largely theoretical and dependent on major physics breakthroughs. Here's a glimpse into the science of future transportation hyperloop, proposed by Elon Musk. This system would use magnetic levitation, maglev, to propel pods at high speeds through a low-pressure tube. Prototypes exist, but global implementation faces significant cost and infrastructure challenges. Quantum teleportation, a demonstrated technique for transferring quantum information, such as the spin of a particle, from one location to another using entangled particles. However, it is not physical transportation and involves moving information, not physical matter. To teleport a human, we would need to know the state of every single particle in their body, which is a mind-boggling amount of information.